starting.
Okay.
Now, there are some questions that I'm interested in that we'll be looking at. Yeah, some questions that I'm interested in, because we just finished looking at the rate of a chemical reaction. The rate of a chemical reaction, well, we went as far as looking at the factors that affect the rate of a chemical reaction. And among the factors that we looked at was the factors that we looked at was temperature, and then within the temperature factors, we had reactions being classified as exothermic as well as endothermic. Yeah, I hope you remember that. Yeah, that's what we looked at. Now, from there, we had the reactions being exothermic, we had the reactions being exothermic. So this question reminds us to getting to know the types of reactions. Yes, getting to know the types of reactions as exothermic, types of reactions as the endothermic. Yeah, so the question says, define the following terms, and the terms that we have today, here on B7 are term number 1, which is called endothermic. What is an endothermic reaction? Then the other one is an exothermic reaction. What is an exothermic reaction? So how do we define these terms? An exothermic, an endo, we're talking about getting the energy inside, So, Siso, are you able to hear me clearly? He goes, Iriko bad. Just one question on Siso, he leaves class. I like that. Okay, so we're saying an endothermic reaction is a type of a reaction where reactants absorb heat. That's one thing you need to know. What absorbs heat is not a product, but the reactant. Or just say is a type of a reaction that involves the absorption of heat. So just say the type of a reaction that absorbs the heat. Is a type of a reaction that involves the absorption of heat. That is an endo, meaning getting to have heat inside of the system. That is an endothermic reaction. What about exothermic reaction? An exothermic reaction is that type of a reaction that gives out heat to the environment. Now remember, there are two things here. There is an environment as well as a system. In thermodynamics, we say a system is the area under study. So if you have a test tube, and then inside of a test tube, you've got calcium carbonate and hydrochloric acid. That inside of a test tube becomes our system. That's the system we want to study. And then outside that test tube is our environment. So we are saying an exothermic reaction is a type of a reaction that produces or that releases heat to the environment. That's one thing we know. So exo, XEX, giving out outside. So the type of heat that releases, the type of reaction that releases heat to the environment. Trying to dramatize it a little bit, we are saying an endothermic reaction absorbs heat within the system. So if you have heat coming from the outside into the system, at the end of the reaction, you expect to have the system with more energy than you started, because much of heat has been imported inside of the environment, of the system rather. What do I mean? I mean this: if you have this one as a system, and the temperature gets to be 40 degrees, when it inputs more heat within the inside, let's say it brings in 20, I'm just trying to give you a dramatized where it's 40 at the beginning, then it has imported in heat. So at the end of the day, you expect to have a higher temperature than you started with, because heat has gone from the environment into the system. And that is the reason as to why if you are to write the diagram, we get to have a diagram which goes like that. This is energy, and then this is time. Let's say time. You get to have a diagram which will have this kind of arrangement, where this here is a product and this is the reactant. The product will get to have higher energy, higher energy than you started, because part of it has come into the system. Just like a human being who gets to have the temperature checked now, it's a 35 degrees, then the time you come to get the reading of the temperature, someone has nyekad. The temperature is very high because that person had absorbed a little bit of heat. That is the point I was trying to exhaust. Then we continue, and it's very important that we understand these types of reactions, maybe even giving examples. Yeah, maybe even giving examples. So the B says, give an example of each of the reaction in nature. Nature, not artificial. Not now I'm in the lab. No, I'm with Mr. Kwao. I'm with Mr. Banda. We're in the lab. We're not talking about laboratory reactions. We're talking about processes that do happen in nature. And we have those major ones that we know. Okay, so the ones that we have here, was give examples of endo, where you get to have the temperature going inside of the environment, is that absorbs.
Evaporation.
Evaporation. Now you get to have the temperature. We get to have the liquid absorbing heat, and then at the end of the day, you get to have that heat weakening the intermolecular forces, thereby letting go of the gases, the individual gases. Yeah, that's okay. And then the other one is photosynthesis. Photosynthesis absorbs the heat. Yeah, so the other one, you can go for that. You can also go for photosynthesis. But again, there's something that you need to understand. there's something you need to understand. Why? What we are saying is that one thing you need to understand is there are two things involved here. When heat is coming from the environment into the system, the environment will have a colder temperature, a lower temperature. The system inside of the test tube will have higher, isn't it? That's the reason as to why when you're seated under the tree, it's very hot, the tree absorbs the heat. As a result, you are under the tree, you find the temperature is lower than someone who is not under the tree. Because under the tree has absorbed heat. As a result, the environment outside the temperature becomes lower than the system. Then the other one here, we can go for respiration. Respiration is one of the processes in nature that produce heat. That's the reason as to why this time around we've got those thermal temperature, those infrared thermometers. You just point at someone's vein, maybe somewhere near the skin, because of the heat that the body produces, the thermometer is able to depict the body temperature. So these are the two processes that you can talk about. Photosynthesis absorbs, that is respiration, produces heat to the environment. Describe the effect of exothermic reaction in the industry on the environment. This was for a grade 12, but the information which was there was a little bit coming from thermodynamics. Because thermodynamics, you're trying to observe the energy difference between the outside the chemical reaction and the inside of the chemical reaction. What happens when we have industries that are carrying out reactions which are producing heat? What is the effect on the environment? We are likely to have temperatures we are likely to result in the temperature of the environment being high. Because we have this reaction produces heat, this reaction produces heat, this reaction produces heat, that reaction produces, as a result, the temperature of the environment becomes very high. I hope you understand that point.
Yes.
So it results in the temperature of the environment to be high. We are likely to do that. And these things happen when you pass near the mine. Machine, this one is well. You pass there, it's very hot. There is noise, even the temperatures are very high. These metals are being cooled down and all that. As a result, you find that after you leave that place, you'll be like, at least now here it's a little bit temperate. Not there, it was very, very hot. It is because of these reactions. I hope we understand each other. Then
yes.
we can go to these ones are very easy. You can go down here. That's the same thing. Okay. Very good. That one is also coming from the rate of a chemical reaction. Something that I did, I think it was a good thing that I did. I pointed out on, I picked out on these questions. The something that we did is even here. Get well soon, my friend. Yeah, so what we're saying here is that this one is also coming from the rate of a chemical reaction, and we know very well that there are quite a lot of conditions that we can do, we can change, things that we can do to the reaction in order to speed up the rate of a chemical reaction. The question says the reaction between 4.2 grams lump of magnesium carbonate is reacting with the 0.1 molar solution of hydrochloric acid. The reaction itself is relatively slow. But we don't know why it's slow. Could be that the temperature here is low, or could be that the magnesium lumps were very big indeed. We don't know. The question, the reaction can be increased. What do you do in order to increase the rate of a chemical reaction? Either by increasing the temperature or by using the catalyst. Other than increasing the temperature and using a catalyst, state any two conditions that can be applied to the reactants in order to increase the rate of a chemical reaction. We're looking at the conditions here. To the reaction reactants in order to increase the rate of a chemical reaction. What do we say? One, reduce the particle size. The particle size must be reduced. Do we agree? That once we reduce the particle size of which one? Is it hydrochloric acid? It's magnesium, of course. So magnesium lump should have the particle size reduced. Which other one can we go for? This one, magnesium, is a solid. Hydrochloric acid is an aqueous solution. So temperature or pressure here is not important. You don't, mnaonepo muntu atenga sugar afaka mumanzi muja, then he wants to compress the water. Doing that, I want sugar to be compressed. I think so we don't need the pressure when you are talking about reactants that do not involve gases. The other one is to increase the concentration. So the other one is the concentration of HCl must be increased. That's all you need to do. That's all you need to do. Yeah, that's all you need to do. Now, the question here is explain how does a catalyst increase the rate of a chemical reaction? How do you explain that? How do you explain?
Just a minute.
Okay. Maybe in the interest of time, what the catalyst does is allow me to do this. When you have that, remember what I said.
Okay, yes, I want to explain now.
What something that I explained about this thing here. Here, the level of the reactant and the product, this change here we call it change in energy. Change in energy between the reactant and the product, which we found by changing energy, we say the energy of the product minus energy of the reactant. This can be computed by considering the energy levels of the reactant and that of the product. But there is this energy here, meaning when you have the reactant, before you go to the product, you need to overcome this energy. You need to overcome it. So why we need a reactant is to make sure that this activation energy is overcome. How do you overcome it? By lowering it. Once you lower it, you get to have these particles colliding in the best way, forming products without encountering the barrier of the presence of the activation energy. So what did I say? What I said was you need a catalyst in order to lower or overcome the presence of the activation energy. So that's what the catalyst does. Meaning those catalysts that work there in order to lower the rate of a chemical reaction, what do? They increase the activation energy so that the reaction becomes very slow. Meaning even if the reactants collide, they cannot form the product because of the energy barrier, that of the activation energy. When you have used the catalyst to lower down the rate of a chemical reaction as a result of increasing the activation energy. So what we are saying is that how does the catalyst work? And remember, it's 1 mark because they know that the explanation is very short. So how does the catalyst work? It works by doing what? By lowering the activation energy of reactants. That's how it works. That activation energy has to be lowered. And the only thing that does that is what? The catalyst. Each of the condition has a role to play. Why do you need to increase the temperature? So that the particles get to have enough kinetic energy and you know the kinetic energy. Hello, Diana.
Hello.
Did you hear what I said? Hello, Diana. Hello. Yeah. Each condition has a role to play. When you say you need a temperature so that these particles get to have enough kinetic energy. You know, when a particle has got kinetic energy, what do they move? They move about. What do? They move about. As they move about, they collide with any other particle. Kinetic energy for human beings is money. Someone might be home 22 hours and the chat will win a lot. I end up booking activation energy from kinetic energy from nowhere. Whether we bera vintu linandrama, nezagula vintu vanga. That is the kinetic energy for human beings, money. But of course, not everyone is able to react in that way. Why do we need to increase the concentration? You are increasing the number of particles that are reacting. When they are a lot, it's very easy for this neighboring particle to find what to react with because they are a lot. Now, when the concentration is low, meaning these particles are very, very far apart from each other. That's why we need to increase the temperature, but the number of colliding particles must be more. That's about temperature. We talked about pressure. Compressing, bring them together. What about reducing the particle size? So that, remember, we're saying matter is made up of tiny particles. So when you have a big magnesium, there are magnesium atoms inside. So for each particle, for each atom to come in contact with water,
Sir, can you get me?
Yes, yes, I can get you.
Hello.
Hello, Dana. I can get you. Hello. Yeah, so that's what we need to do. I hope you understand that. That's what we need to do. That is what the question here is trying to say. Now we go to what we're learning today. What we're learning today was the Haber process. Very soon you'll come and learn the contact process and how all that is done. Now, if you look at the Haber process in the best way that we did, So the Haber process is a process that involves the reaction between nitrogen as well as hydrogen in order to produce NH3. What name is given to our NH3? Ammonia, not ammonium, but ammonia. Now, before you go anywhere, let's try to see if we can recall the reaction. So we have hydrogen, or you can start with nitrogen, doesn't really matter. You can start with nitrogen 2 plus hydrogen 2, and then remember the reaction is reversible to form NH3. All these gases, them all gases. But the most important thing we need to do is to balance the chemical reaction, chemical equation. And how do we balance it up? We look at the number of hydrogen, nitrogen atom here are 2. Here we only have 1. So we're going to put a 2 here. So that here there are 2, and even here there are 2. But it's not going to end well because we have now added more stress, even on what? We've added more stress on nitrogen, on hydrogen rather. So hydrogen 2 and 3, they are 6. But how many are here? 2. So the only number that you can multiply with a 2 to give us 6 is 3. So this is a balanced chemical equation. Now, the question, Diana, can you confirm if you're getting us?
Hello.
Hello, Mwari.
Hi, sir.
The presentation is underway, so whatever you have missed, you're going to have it sent to you. Diana, can you confirm if you're getting us? Okay. Yeah, so that's what I said. Now, the question says, this equation was balanced, but the coefficient, they did not put numbers, but they had just put letters. So which letter, according to the question that we've done here, and the one that was done here, which letter is being represented by A? The coefficient of hydrogen, definitely it's a 3. So we're going to have a 3 here. And look at the coefficient of ammonia here, NH2, the coefficient is 2. So we're going to put a 2 here. Now, the question you might ask yourself is, since there's no half mark, 2, but they have given you 1 mark, what happens? It's because even if you balance it here nicely, here the coefficient is wrong. Have you balanced the equation? So for as long as one is wrong, then the other one is wrong. That's the bottom line here. We cannot have one species balanced, the other one not balanced. For as long as we put a 3, here we put a 4. We're going to say that hydrogen will be 8, and then hydrogen here will be 4. So we're not doing anything. So we have to make sure that whatever we are doing, we do it in the best way. I hope we understand. Very good. Now, the last part here says, apart from temperature, I remember that's how the teacher used to read. Some of us was really difficult, temperature. You want to put CHA. So we'd read it temperature. So there's temperature, pressure, and the catalyst in the Haber process. And remember, just from learning this today, where we said the pressure is about 350 Pascal, 350 atm. That's the pressure. Then the temperature was 350 to 300 to 450. Yeah, to 450. To 450. So just say about. That's a beauty here. So just say about 550 degrees centigrade. That's the temperature. And then we know the catalyst. The catalyst is Mr. Famous fine ferrous, fine iron. Okay. So the question here says, apart from temperature and the catalyst, mention one other. Now, let me guide you here as an examiner. When they say mention, do you mention the name of the best friend? Do you specify where Mapesho stays? You're just mentioning the name. Now, in case you say Mapesho, and then you say he stays in George compound. Mapesho doesn't stay in George compound, meaning you have disqualified your answer. If they say mention, my dear friends, here, just say pressure. We are mentioning. Now you want to sound educated. I said, hey, but the pressure is 400 atm. The question is, have you answered the right thing? You have disqualified because this is not the pressure. And to start with, they didn't ask you to give the figure. They just said, mention it. So it is very, very important that we understand the statement behind the question. Mari, my friend, have you gotten what I just said here?
Yes, I have.
Good. And by the way, my patient is greeting you.
Oh, hi.
Bye. Okay, so that's how the work here was supposed to be done. Questions? We can go to this thing here. No, first let's do the ones that we did in class. Not even this one here. Not even this one here. There we are. Because we are remaining just about 7 minutes, so it's better we focus on those ones that we've learned. And I like doing these, my polymers, my benzene, my cyclohexane, my polycyclobentane, my zinc benzonate. Yeah, so that's the question that we have now. A true reflection of what we learned. So these guys at times they are very fun. You see where the question came. They have given us a catalyst. They have given us the conditions. Now this time around, we need to specify the quantity of these conditions. So the question here says, nitrogen is used to manufacture ammonia. And we know that it's not nitrogen alone. It's not alone. There must be another gas. And they have given us a sketch diagram. We have nitrogen, gas X. These two guys are added together. When they are added together, but we know for sure that when these two guys are added together, the first thing that should happen is that they must be compressed. When they are compressed, then the gases must be passed over to another chamber where they will be converted in the presence of a catalyst. And after that, we're going to have the gases being formed, ammonia being cooled. But now, someone asked me a question to say, why is it that, I think it was in Chimunya, even after these gases have been compressed, you need a converter? Why do you need a converter? My question is, at times I don't answer questions in a straight way. I'll try to dramatize it a little bit, give you a situation, then you understand. There is Mr. Man here and Madam Woman. These idiots have been dating for quite some time. Compressed, right? Compressed. They have been dating and they move along. They move along. Just because Mr. Man went through the girl's phone, where my messages are. Jesus, even the devil was scared to look at. What happens? These guys will break up. This one will go his own way and this one goes out. Is there any marriage which has resulted? There is no marriage. But these guys were compressed. And remember what we said according to the kinetic theory, is that for a reaction to take place, for a product to be formed, some things must be present. One, there must be particles to collide. Particles to collide. So these particles are going to collide during the compression. Yeah? Particles must collide. And when they collide, there must be enough energy, sufficient energy. We know that a reaction is all about bond breaking and bond formation. And you know that there's a form of energy which is associated with bonds, chemical energy. Yeah, so there must be enough energy. It's something that I even dramatize it in class to say there may be Madam B and Mr. K. These people have been illegally married for some years, but there's no child. There's always been some form of collision between them, but there's no child. It could be that the doesn't involve enough energy. Could be that the collision doesn't involve enough energy. And then we say these particles must collide in a proper orientation. These conditions must be there for the product to be formed. Even cooking in shima, when there is no enough energy, there is no heat energy. Can you have enough shima? Could it be? Proper orientation, the tackling of shima, kuchakulization, you need to do it in the nice way. Even when the heat is there, particles, water, and medium will collide. But for as long as there isn't enough tackling, the shima won't be eaten in the best way. So that's what I'm saying. For the product to be formed, there must be those things. Particles must collide in the proper orientation. There must be enough energy, and they must also be. They must collide in a proper way. There must be sufficient energy, and of course, the other one that I mentioned. So that's why we needed a converter. A converter is there to make sure that those that collide are checked. Guys, you and I, do you have enough energy? Get married, go and produce nitrogen. You don't have enough energy, go back and be reconverted because you didn't have enough energy. So that's what we have in the many minutes says, name the process shown above. We know that the process here is Haber process. Haber process. You know, it's important to understand even the process. And then B says, state the substance represented by X. We know that nitrogen must react with hydrogen. Hydrogen. Write the condition represented by X and Z. We already know the catalyst, so they haven't told us to write the condition. Now here, it's important you quantify. Degrees centigrade. Can you mention here? Can you, so many when you put Y, you're going to say temperature, degrees centigrade. You give the value. So you say Y is equal to temperature, and then you quantify about 350 degrees centigrade. ZD is a pressure about 350 atm because they have given us the units. So it's important that you give the value, the numerical value of the item itself. Name the catalyst used. The catalyst used is fine iron. It's iron. Construct a balanced chemical equation for the reaction